So when we're looking at the graphs, and I highlighted it a little bit before, this is an important concept. It's true for all exponential graphs. Okay, the base graph always have a point that is in common, and I pointed that out right here. So all of these graphs are going through the point 0 at 1. They have the same y-intercept. That's important to notice and remember. So which of the relationships shows growth? Well, we already talked about that. Growth as we're going from left to right means that you would be increasing your y values. As x values increase, y values increase. So C and D represent growth. And then which ones represent decay? Exponential is when you get into that idea of half-life and radioactive decay. That's all your exponential talk. So that's why we use it as growth and decay. Also, when you're talking about finances, your finances can decay. You lose money in them. So the decay relationships are the ones as x gets large, y gets small, 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 small. So that's our A and our B. And if you were going to write anything down right now, I would write down these key ideas because this is the main crux of those graphs. So the y-intercept 100% of the time is going to be at 0, 1. It doesn't matter what kind of graph you have. It doesn't matter if your base is a whole number. It doesn't matter if your base is a fraction. Doesn't matter if your base is really a really big whole number or a really small fraction. They all go through that same y-intercept. The graph of an exponential relation in the form of that does not have a 0. I'm so excited, but I'm remembering I'm videotaping. Okay. So it never crosses the x-axis. Okay. Then the growth or the decay factor is the base of the power. So if we're looking at this example here, the base is the A. So when we were up here, we were talking about, oh, the base is 2, the base is 5, the base is 1/2, the base is 1/5, and we looked at the differences in those graphs. Okay. So there are two types of exponential relationships. There's an exponential growth, and there's an exponential decay. You have a growth relationship if your A value is a number bigger than 1. So if it's a whole number base. You're going to have something that's growing. If A is greater than 1, the graph increases very slowly for the negative x values and increases rapidly for the positive x values. So what does that mean? Well, let's look at the red and the blue. It increases really slowly, 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 slowly. Oh, kind of getting faster, kind of whoa, and there it goes crazy. Even more for the red. Like this is even slower growth. And if you look at the numbers between red and blue, the 2 has a quicker growth on this side, but a slower growth on this side. And the 5 has a slower growth on this side, but a much quicker growth on that side. So just interesting relationships to notice. Same thing happens if we go the other way. The bigger the value of A, the steeper or the quicker, the faster the growth. The faster the growth. So then if we switch gears and we talk about decay, that's if we've got a fraction base. And it says here a number that's in between 0 and 1. Well, that's what a fraction is. A fraction is a decimal number between 0 and 1. Okay? So if the graph will decrease very rapidly for negative x values, and then decrease slowly for the positive. So it's the exact opposite of the growth. The decay is just flipped. And if we look up here, that's green and purple. They drop really, really quick when the x values are negative, really quick drop, really steep drop, and then slowly, slowly, slowly on the other side when x is positive. The smaller the value of A, the steeper, I'm going to say the faster again because I said faster in the other one, the faster the decay. All right.